All right, here we go. We're on page 180 or so of your workbook, depending on which version of the workbook you have. Today we're going to get through concavity, inflection points, and second derivative test is all together here. So moving forward, so we've been looking at first derivative. Tells us where a function is increasing or where it's decreasing, and we've gone through the process of how to find a first derivative. We've gone through the process of how to find a second derivative. Today we're going to look at what the second derivative is going to tell us about a graph, and it's going to tell us about a function and how it behaves. So here we go. We have this nice curvy function. It's called f of x, and it says, consider this following graph of f of x. In general, the graph of f of x is called concave downward on an interval if f of x lies below its tangents on that interval. In the example above, f of x is concave down on the interval. So at c, this concavity changes. And so it is concave down on the interval negative infinity to c. What that means, kind of a loose interpretation of what it means, is that rain would slide off. If it's raining on your function, rain would slide down and it would slide off this concavity. A more technical definition, what it says right here, is it's saying if the function lies below any tangents. So any tangents that we would have, the curve is below those tangent lines. And so there's our technical definition of concave down, is if the curve is below your tangent lines. It says it's going to be concave up on an interval of f if f of x lies above its tangent lines. So technically our definition is if we draw tangent lines, if the function is above those tangent lines. So then it would be concave up. A more casual definition would be, it's going to catch rain. So concave down, rain slides off it. Concave up, rain is going to be caught by this. I know it's not really rain, but it ends up being kind of a casual definition that really quite works with this. So this one is concave up on the interval from c to infinity. So that's how we think of concavity. If a curve changes concavity at c, then it is called a point of inflection. C comma f of c is an inflection point. That's going to be this point on our graph here. We've seen inflection points before when we had y is equal to x cubed or something like that. When we had a multiplicity of 3 or of 5 in a polynomial, if we had that going on, that was called an inflection point. It doesn't have to happen where the slope is 0. And in fact, now we start to see an inflection point can be where the slope isn't 0. All it has to be is it ends up being this change in concavity. This y is equal to x cubed. We can see this part here is concave down. Rain would slide off it. Whereas this part of this curve, this is concave up now. Rain would be caught by that. All right, so moving forward. Let's examine the following. You can use a graphing calculator if you have one. We're going to sketch the curve of 1/10 of x plus 7, x plus 1, x minus 5. We're going to draw what this looks like for f prime and f double prime on the same sketch. And the first and second derivative indicates different things about your original function, f of x. Okay. So what our function is going to look like. So take a minute, hit pause, and let's start to sketch this and see what this looks like. So we have a cubic function. It's going to look like this. It's going to have x-intercepts at -1 and at -7 and at +5. So it's going to kind of look like this. It has positive leading coefficient. So our original function f of x is going to look something like that. but of course go through this point. Sorry about that. There we go. Okay, so that's what we know so far. So ignoring what the scale looks like, that's kind of what's going on. We could find a y-intercept really pretty easily, and there it is. Okay, so that's what y equals f of x looks like. If we're wanting to consider what the first derivative looks like, remember the first derivative is going to have a 0 wherever our original has a slope of 0, because our first derivative graph is the slope, so it's going to look like that. And if I'm sketching this part of our original curve, this part of original curve is increasing, which means my first derivative is going to be positive, which means it's going to be above the x-axis. So it's like this. And then in our next interval, this is decreasing. While this is decreasing, our first derivative is going to be negative, so it's going to be down below the x-axis. And then in this last part of this is increasing again. And so if it's increasing again, that means our first derivative is positive. So here's my graph of y is equal to f prime of x. Now, my second derivative just ends up being the derivative of f prime, really. And so what we end up with is and I suppose this should be, we're going to look at where my first derivative has a slope of 0. Where my first derivative has a slope of 0, we're going to end up with a 0 on our second derivative. My first derivative is, this is decreasing. This is decreasing, which means the slope of it, which means my second derivative is going to be negative. So it ends up being looking like this. It's negative, it's below the x-axis. And then my second derivative is going to be above the x-axis when my first derivative is increasing. My first derivative is increasing all through here. Therefore, my second derivative is positive all through there. And it ends up being a straight line. It's going to be linear. This is degree 3. My first derivative is degree 2. My second derivative is going to be degree 1, because obviously the degrees decrease by 1 each time you take a derivative. So this straight line is f double prime of x. So that's what it looks like. When we look at our sketch, and so on the next page from your sketch, we should be able to conclude about concavity. So I'm just going to keep it on this graph for this note. Concavity, note f double prime is the rate of change of f prime of x, the graph of a twice differentiable function y equals f of x. It's going to be concave up when f double prime is greater than 0. So this linear function is greater than 0 here. That means my original function is concave up on this interval. So y equals f of x is concave up when the second derivative is positive. When the second derivative is negative, when the second derivative is down here, that infers that we have concave down in our original graph. So this part is concave down until our second derivative is 0, and then it ends up being concave up. And so we will have intervals of concavity, just like we had intervals for increasing and decreasing. And so let's start to fill in this note. It is concave up when f double prime is greater than 0. If it's concave up, if it's catching rain, then there should be a relative minimum on that interval. If it's concave down, when f double prime is less than 0, therefore you should have a relative maximum on that interval. To find possible points of inflection, we look to see where f double prime is 0. So we're going to have a point of inflection where or a possible point of inflection, I should say, where your second derivative is 0 or where your second derivative does not exist. These are not called critical numbers. We reserve that term for first derivative test, but they kind of, we're going to treat them similarly, but technically they're not critical numbers. What this ends up inferring is we have the second derivative test. This is a test for relative extrema, like your first derivative test, but not a test for concavity. If f prime of x, if f prime of c is 0 and f double prime of c is positive, then it has a relative minimum at c. What this is saying is if our slope is 0 and our second derivative is positive, if our second derivative is positive, that means it is concave up. And if we have a slope that is 0, then we have a minimum at C. So we will have a minimum where we have positive concavity, or where we have concave up, and we have a flat point if we have a slope that is 0. If your slope is 0 and we have the second derivative is less than 0, therefore it is concave down. It's going to, of course, have a maximum at C if it has a slope of 0 at that point and is concave down. Note, the test will not work for f double prime of C is 0 or does not exist. If this happens, we have to go back to the first derivative test. Second derivative test is great for polynomials. If you have a more complex function, it's best to stay with our first derivative test. So to summarize what all of this looks like, if f prime of x is greater than 0, then it's increasing. If f prime of x is negative, then the function is, of course, decreasing. No big deal. We've known that for a while. And if f prime of x is 0, then it has a possible relative max or relative min. When we refer to extrema, relative extrema, that is a general term for max or min. They're extreme points. Now our new stuff is f double prime is positive, then it is concave up. Where f double prime is blank, then the function is concave down, therefore it is negative. F double prime is negative, we have concave down, and then if it's 0, we have possible point of inflection or inflection point. All right, so what does this look like altogether? We've got 4 examples. Determine the relative extrema, concavity, and any inflection points for the following functions. Number 1, let's start with number 1. Of course, we are going to look at 1, f of x is equal to x cubed minus 3x plus 1. So first, let's find our first and second derivatives. Super easy. It's just polynomial. So 3x squared minus 3 f double prime is 6x. Our critical numbers. Our critical numbers, we let f prime x equals 0. 3x squared minus 3. 0 equals 3, bracket x squared minus 1. 0 is equal to 3. X plus 1, x minus 1. So x equals plus or minus 1 for the critical numbers. Not a big deal. F prime of x, let's draw our number line. Let's label what our number line is measuring. So this is measuring first derivative. We have critical numbers at -1 and at +1. And what happens in our intervals? If we have x is -2, then this would become 3, which is positive, times -2 plus 1, which is negative. This is positive times negative 2 minus 1 ends up being negative, makes this interval is positive. Between negative 1 and 1, when x is 0, then it's just negative 3, of course, and so this ends up being negative in that interval, and then it ends up being positive after that interval. We have a function that is increasing. We need to label this every time, please. Increasing. It is increasing on negative infinity to negative 1, union 1 to infinity. It is decreasing in between on the interval negative 1 to 1. Round brackets because it doesn't include those points. We have a relative maximum when we have increasing and then decreasing. So we have a relative maximum at when x is negative 1. What's our y value? For our y value, we have to go back to this, and we're going to look at f at negative 1. We plug negative 1 in for x. This becomes negative 1 comma 3. We have a relative min when we are decreasing and then increasing. We have relative min at 1, and we plug that in into our original function. Our original function is going to tell us a point, right? So at 1 comma negative 1, I believe. We should label a possible point of inflection. Where does that happen? We have a possible point of inflection. Possible point of inflection when x is 0. Because our second derivative is f double prime of x is 6x. So when that's 0, it makes it 0. So f double prime of x. Number line looks like this. There's 0. 6x, so when it's less than 0, this ends up being negative. Second derivative is positive when x is greater than 0. So therefore, let's, just like we did with increasing and decreasing, let's label concavity concave down. It is concave down on the interval negative infinity to 0. It is concave up from 0 to infinity. We have an inflection point. We have an inflection point at 0, comma 1. Okay, so that's it for question number 1. We have determined our relative extrema, our concavity, and any inflection points for the following functions. So we move on. Question number 2. F of x is equal to x to the 4. So f prime is 4x cubed, and f double prime is 12x squared. Critical numbers. Zero is equal to 4x cubed. Quite clearly, x equals 0 is it. This is my number line for f prime of x. If this is 0, then to the left of this, when x is negative, this ends up being negative slope. When x is positive, we will have a positive slope. So therefore, increasing, let's start decreasing on negative infinity to 0. It is increasing on 0 to infinity. We have a possible point of inflection, where 0 is equal to 12x squared. So x is 0. So we look at this, and we see that our number line looks like this. So we have a possible point of inflection at 0. But when we look at our second derivative, 12x squared, when x is less than 0, this is positive. When x is greater than 0, this is positive. So because our concavity doesn't change, we don't have an inflection point there. Back up a second here. What's one thing that I missed? I did miss that I had decreasing and I had increasing, but I didn't state back up here. I didn't state my relative. It's decreasing, then it's increasing, so we have a relative minimum at, sorry about that, at 0, 0. We should finish off by concluding this is concave up. From negative infinity to infinity. All right, number 3. Let's move to the next page. 3, it tells me that f of x is x to the 2/3 and 6 minus x to the 1/3. We are asked to find the first derivative ourself, and we will need product rule. So product rule for that says I'm going to have 2/3 x to the negative third. When we subtract 1, g stays the same, 6 minus x to the 1/3, plus f stays the same, x to the 2/3, derivative of g. Derivative of g ends up being times 1/3. Inside stays the same, subtract 1 from our exponent, 6 minus x to the negative 2/3, and then don't forget to take the derivative of the inside function. So this is times -1. I'm going to common factor here. I'm going to common factor what's my lowest degree of x is I have x to the negative 1/3 here. I have x to the positive 2/3 here. And so I'm going to common factor out x to the negative 1/3. What else am I going to common factor? I have 6 minus x to the 1/3. I have 6 minus x to the negative 2/3. I'm going to common factor out 6 minus x to the negative 2/3. I'm also going to common factor out, I have a factor of 2/3 here. I have a factor of negative 1/3 here. I'm going to also common factor out 1/3. And what does all of that leave me behind with? In this first term, it leaves me behind with 2 from here. This term here is gone. The 6 minus x to the 1/3 is now 6 minus x to the positive 1. And then our second term, this is minus. We've common factored out 1/3. Common factor out x to the negative 1/3 means we are left behind with x to the 1. And that 6 minus x is all gone. There's my first derivative. Let's go ahead and simplify this. Downstairs we have 3 times x to the 1/3 times 6 minus x to the 2/3. I'm just going to leave it as an exponent here for now. And then what do we have left upstairs? We have 2 times 6 minus 2x minus x is 12 minus 2x. Nope, minus 2x minus x is minus 3x. We can divide both top and bottom by 3. Leaves me with 4 minus x over x to the 1/3, 6 minus x to the 2/3. And there's my f prime. We are given what f double prime looks like, so we don't have to do that one. All right, critical numbers. Where is this either equal to 0 or where is it not defined? It's equal to 0 when x is 4 because of the numerator, because the denominator, x equals 0 is going to make the denominator 0. X equals 6 is going to make the denominator 0. So those are our critical numbers. So we need to look at f prime around all of those points here, 0, 4, and 6. All right. When x is less than 0, when x is, say, -1, when x is -1, the numerator is positive, the denominator is x -1 to the 1/3 is negative, and then 6 minus -1 is 7 to the 2/3 is positive, makes this negative in that interval. Between 0 and 4, so say a number like 1, then this is going to be 4 minus 1 makes the numerator is positive. 1 to the 1/3 is positive. And then 6 minus 1 is 5 to the 2/3, which is also positive. So in this interval, we have positive values. Between 4 and 6, say a number like 5. If x is 5, 4 minus 5 is negative. 5 to the 1/3 is positive. 6 minus 5 the 2/3 is positive, makes this is negative. And then my last zone, when x is greater than 6. When x greater than 6, maybe a number like 7. 4 minus 7 is negative. 7 to the 1/3 is positive. 6 minus 7. 6 minus 7 is -1, but it's to the 2/3, so we are going to square it and then cube root it. So that makes this is positive. And so altogether, that ends up being negative in that zone. So increasing on 0, 4, decreasing on -infinity to 0, union 4 to 6, union 6 to infinity. There's some discussion about whether we can just go 4 to infinity, of whether it ends up still being decreasing or not. There are different thoughts about that, because what exactly is happening at 6, it depends. If that's a vertical asymptote, then we would have to break that up into 2 intervals. If it ends up being an inflection point that it's decreasing and then decreasing some more, that it just so happens to have a slope of 0 in between, well, then we could call it all decreasing. But I think this is going to have a vertical asymptote there, so we have to break that apart into 2 intervals of decreasing. All of this means we have a relative maximum when it is increasing and then it's decreasing. So we have a relative maximum at 4, at x equals 4. If we run this through our original function, that means f at 4, so this is going to get a little nasty in here. F at 4 is equal to 4 to the 2/3 times 6 minus 4 to the 1/3, which is cube root 16 times cube root 2. If we want to write it like this means 2 to the 4/3 times 2 to the 1/3, then that maybe makes some more sense that that's 2 to the 5/3. We could simplify that radical and get the same thing that way. So therefore, we have a relative maximum at 4, 2 to the 5/3. We have a relative minimum where it goes from negative slope to positive slope. At 0, we have a relative min. At 0, this one's a little easier, 0, 0. All right, second derivative. So we are given in this question, second derivative is equal to -8 over x to the 4/3 times 6 minus x to the 5/3. A little bit of nastiness in here. We have possible points of inflection. Where? When x is 0, this is undefined. When x is 0, it's also undefined when x is 6. So we're going to look at those. We're going to look at f double prime. We have 0 and we have 6 as your possible points of inflection. We plug those in for f double prime. What do we get? The numerator is always negative. When x is -1, say, x to the 4/3 is positive because we have an even numerator in that exponent. 6 minus -1, the 5/3, so that ends being positive, makes this zone is negative. Between 0 and 6, when x is 1, what do we have? We've got -8 is always negative. 1 to the 4/3 is positive, and 6 minus 1 to the 5/3 is positive. So this zone is negative. And then when x is greater than 6, when x is greater than 6, -8 is always negative. When x is greater than 6, we're looking at a number like 7. 7 to the 4/3 is positive. 6 minus 7 is -1 to the 5/3 because the numerator is odd. This is going to preserve the fact that it's negative, and negative divided by negative makes this positive in that zone. So therefore it is concave up. On 6 to infinity, concave down. On negative infinity to 0, and then 0 to 6. Our slope is undefined at 0. We have a point of inflection. Not at 0, but at 6 we do. Changes from negative to positive concavity. And so we have 6, 0. Woo! Lots going on with that question. Number 4. Maybe pause the video, take a minute to stand up, breathe, stretch. There's a lot going on in there. Number 4, f of x is equal to x cubed minus 9x squared. This one looks like it's shaping up to be maybe a little easier for us to get our head around, at least the derivatives. This is just polynomial, so this ends up being kind of nice to work with. X cubed minus 9x squared plus 15x minus 5. First derivative, no big deal, 3x squared minus 18x plus 15. second derivative 6x minus 18. For f prime, we get, if we're looking at, to find our critical numbers, we're going to make f prime of x, we're going to make that equal to 0. So 0 is equal to 3x squared minus 18x plus 15. Let's first divide out 3. Whether you just leave it as common factored out 3, or whether you, because it's equal to 0, so you can divide, but x squared minus 6x plus 5, let's just leave the 3 there, it's not doing any harm. X minus 5, x minus 1. That way that's still our first derivative function. So we have critical numbers. Where our first derivative is 0 or undefined. So we have critical numbers at x is equal to 5 and x is equal to 1. We have f prime number line looks like this. Here's 1, here's 5. And this just ends up being, so when x is 0, it's, well, even just looking at this, it's positive 15 makes this positive. Between 1 and 5, so when x is 2, we get 3. 2 minus 5 is negative. 2 minus 1 is positive. And it's a product of those things. And then when x is greater than 5, what do we have when x is greater than 5? This is 3, which is positive. Greater than 5 means 6 minus 5 is positive. 6 minus 1 is positive. So positive, negative, positive. We are increasing. On negative infinity to 1, union 5 to infinity, we are decreasing. On 1 to 5, we have a max. Rel max. Yeah, it's where it's increasing and then decreasing. So at 1, we stuff 1 back into our original function in f at 1, and we find f at 1. This gives us 2. We have a relative minimum where it's decreasing and then increasing. So at 5, we have a relative minimum. At 5, this gives us a value, f at 5 is negative 30. All right, so second derivative, f double prime. It's going to equal 0. If I factor that, that's 6 times x minus 3. So you have a possible point of inflection at x equals 3. We look to see what happens to the left and right of 3, and what do we get if 6 times x minus 3, this will be negative. When x is greater than 3, that ends up being positive. So therefore, concave down. Concave down on negative infinity to 3, and concave up on 3 to positive infinity. Do we have a point of inflection there? Does the concavity change signs? Yes, it does. And so therefore we have a point of inflection. How do I spell? Point of inflection happens at 3. So 3 comma, running that through f. F at 3 is 14. And that is it. Ladies and gentlemen, that is it for this section. So this is second derivative test and concavity. Pretty big idea, this whole idea of concavity. But whether you're looking at concavity, its definition of whether the function is above or below its tangent lines, or whether you think of rain sliding down it or not. That's kind of what's going on with here. So second derivative test, super handy for sketching. All right, that's enough for now, and I will see you in the next video.